So many times. Okay. All right. Let's get started. So this is lab 2, Volcanoes Lab 2, lab 6 overall. So that should be halfway. So you guys are doing well. I should have started with this. So for this lab, I'll just make a quick note right away at the beginning. So the last question, question 25, is going to be asking you to show your work for questions 3, 19, and 21. So just while you're going through, just maybe make a note of those 3. So you know to like write down your actual work on a piece of paper, on a laptop or something, just so you don't have to come back to it later. Just like a picture just to kind of show what you did. Okay, so this lab is going to be looking at 4 different types of volcanoes. So image 1 here, this is called a cinder cone. It's built up by a lot of ash typically. Number 2, this is called a stratovolcano, sometimes called a composite cone. And they tend to be very, very steep, and they're built up with all this pyroclastic flow material and lava and just all that kind of volcanic material, so that allows it to get pretty steep typically. Number 3 here, this is called a shield volcano. These are really common in Hawaii, for instance. Very, very gradual slope. They're mostly built up with just lavas. So because they don't have as much of that ash, they don't tend to get as steep. And then number 4 is called a caldera, which is when a volcano erupts and the magma chamber in here, when it gets emptied, when it erupts, since it has that open space, it sometimes collapses in on itself. And we get this big open space at the top, and it's pretty common for it to like fill up with a lake, which we see pretty frequently. So this image is where all the volcanoes are that we're going to be looking at in the lab today. So we're looking at all the types of volcanoes. So the point of the lab is to compare different slopes and see are they similar or different and whatnot. So we have shield volcanoes, calderas, stratovolcanoes, and some cinder cones. And then the cinder cones A and F here from the same actual caldera, they're cinder cones within that caldera, which can happen sometimes. So at Okmok here. But we can still calculate slopes for both of them. Cool. So we're going to be calculating slope gradients, which we can get by the rise over run of a triangle. So we can think of this as half a volcano. So the slope over here, we would have the like opening here, and then it would drop down on that side. And we can get the slope gradient by calculating the rise, which is the height there, and the run, which is the half length of it. And then the lab describes subtracting the max minus min, which doesn't really make sense on this image, but it will on actual volcanoes that are above sea level. And I'll show an example of that. But this rise would be 3, so the top is 3, the bottom 0, 3 minus 0 is just 3. And then this length here is 36, so we can get a slope gradient by taking rise over run, that'd be 3 over 36. We can simplify that down to 1 over 12. That's where that 1 over 12 comes from. And then we can find a slope percentage by dividing that out. So 3 divided by 36 would get, this is the slope gradient in decimal form, and we can multiply by 100 to convert it to a percent, 8.3%. This would also work with 1 over 12. You get the same thing. And then this is an example of a real life volcano, which doing the same thing. You would want to find rise over run, and the lab is going to ask all this different info. So make a note of all of it. And then this is where we need to start taking into account the max minus min. So the max for this one being 411, we'd want to subtract that out by 398. We get a rise of 13, and then run, it would be 50 minus 16, a run of 34. You'd want to be finding positive numbers. So if you're finding negative, you did it backwards. 13 over 34. We could divide that out to get this slope gradient in decimal form of 0.382. We can convert that to a decimal by multiplying by 100. And so I should have mentioned it at the beginning, but this triangle here comes from this image on the right, which is just a top image of this volcano that we're working at, the St. Michael cinder cone. This line here is for this bottom image, this slope gradient. And we calculated this part right here. So that's where this data comes from, where we can see these heights. But yeah, so we found a rise over run. We can divide that out, multiply by 100 to convert to a percent. And then from there, we can find an actual slope angle by going up to table 3 and finding kind of where that's the most similar. So they won't always match up perfectly. Like this one's kind of on the line between being close to 37.5% and 40%. It's kind of up to you if you want to kind of pick something in the middle or just pick what's closest. I'm fine with either. I just said 20.6 for this because it's pretty close to 37.5. You can also find the slope angle by using trigonometry. I think for this, you should be able to take the tangent as well to find the slope angle, but you don't have to, just so you know where the math is coming from. But you can just use this table. And so before I jump into this, let me just oh, darn it. Kind of make sure we're on the same page. Okay. So the lab is going to be asking for the rise and run. We can get that from here. So we'd want the max minus min, so 411 minus 398. That would be the rise. Then run, 50 minus 16, that'd be the run. So you'd want to put those in. That slope percent, you'd want to take rise divided by run. That would give you the slope gradient. We can multiply that by 100 to convert to a percent. Once you have that, we can find the slope angle by coming up to table 3 here. And it was like 38, so close to around 37.5 on this table, a slope angle of 20.6. So that's saying that this angle here is 20.6. And it's very repetitive. You're going to do the same thing for a bunch of them. And the whole point is to try to compare the slopes between those 3 types of volcanoes I mentioned. And then after you do that, we're going to want the average slope angle between the 3 types of volcanoes, that shield volcano, that stratovolcano, and the cinder volcano. And we can just find the average by taking the sum of each slope and dividing out by the number of volcanoes. So I believe we have you do 3 volcanoes of each type. So it would be the 3 angles divided by 3. And then we can kind of compare from there, like which ones are the most gradual, which ones are the steepest. Not too bad, hopefully. And then the next part of the lab is going to be looking at caldera volume calculations. So once again, a caldera is when we have this magma chamber here, the volcano erupts because there's an open space now, the rock's not supported, so it will collapse in on itself, and then it'll rain. We get lakes a lot of times. There's a picture of the top there of a caldera. And then we can find the caldera volume with this equation here, height times pi times radius squared. Let's see. So just be careful here, the height we give the data for this, but it's not the 2,100. You're going to have to take the difference just like we did with the other calculations. You'll have to do the estimated original height minus the elevation of the caldera floor. Because if it was 2,100 meters, that would be saying that it's the height of the volcano down to sea level, and that's not accurate. It's not quite that tall. So we'd want the difference of those two, and that's the height that we're using in this volume calculation. So you take what you find there, you'd multiply by pi, and then we give you the radius. And then just don't forget to square it in a calculator. It might help to put parentheses around the radius so it doesn't mess up on you. And it'll be a really, really big number, so don't be spooked by that. It'll be pretty big. And then the last part is looking at ash volume calculations. You'll take the magma volume calculation that you just found for the last questions and multiply by 2. So not too bad. But I believe for this, we only ask for the Okmok eruption. So just make sure you did the right one for this ash volume calculation. And it'll be a really big number as well. Give some examples of ways to express it. Just whichever way you feel comfortable. If you want to write it out or you want to do it the more like scientific way, that's fine. But either way, it'll be really big. Let's make sure I'm on the same page here. Yeah, so for this part, we give 2 different volcanoes. We want the volume of the magma for both of them, but you only need to do the ash one for the Okmok. Yeah. All right, and then, oh, yeah, Okmok ash here. And then the last part here is a volume scavenger hunt. So you want to go find an object that's roughly 1 meter by 1 meter, that's roughly 3 feet by 3 feet, and just kind of write an object that kind of fits that description. I just threw up a picture of like some furniture that looks maybe like it fits. This looks maybe 3 feet across. It doesn't have to be perfect. And then the whole point of this is to try to picture how many of these objects can fit within that like ash cloud for the Okmok eruption. It's going to be really big, obviously. I don't expect you to get it perfect. I don't even know, but give it a guess, put a number. And then, yeah, just make sure that while you were going through, you wrote your math out for questions 3, 19, and 21 and upload a picture of that. And that's all we need. Okay. All right, that's all I have for you. Please let me know if you have any questions.